Good morning, Internet. I am Matt Buyak, and in this video we will finally be taking a look at problem number 60 from the Project Euler problem archive. Now, this problem asks us to find a set of 5 prime numbers such that any two numbers in the set, when you concatenate them in either order, will give you another prime number. And in particular, it asks us to find the set of 5 prime numbers with this property that has the lowest sum. Now, there are two things that are noteworthy about this problem. The first is that it is the lowest numbered Project Euler problem with a difficulty of at least 20%. So we can definitely expect a challenge today. The other thing that is noteworthy is this is an example of what I call a hackable problem. We've had a number of these. I think problem 44 was the last one that made an appearance. And the reason I call it a hackable problem is that it sort of encourages you to take a guess and check approach to the problem rather than solving it in a way that's provably correct. And I think there's usually 3 things that go into a problem being a hackable problem. The first is that it's an optimization problem. That is, there are potentially many solutions to the problem, but you're looking for the best solution based on some criteria. So in this case, we're looking for the lowest sum out of the candidate solutions. The other thing that makes a problem hackable is that the solutions are relatively rare. You can imagine if there were thousands or millions of solutions, you're going to have to find some way of narrowing that down. But if there's only 1 or 2 solutions, maybe you just try each one by putting it into the website and see if it tells you that you have the right answer. The third thing that makes a hackable problem is that finding a solution is much, much easier than proving that it is the best solution. And that is definitely the case with this problem. And so actually, I'm going to split this problem into 2 videos. In this video, we're just going to be concerned with finding a solution, any solution. And in the next video, we'll look at how we can prove that that solution is actually the best solution. Now, typically when I do one of these videos, I'll spend a few minutes describing the approach that we're going to take to the problem and then jump right into the code. But in this video, one of the reasons why it took me a while to come out with this video is that that's not going to be enough. We're going to have to learn a little bit of graph theory before we're ready to understand the solution to this problem. When I say the word graph, you might think of something like this, x-axis, y-axis, points and lines in space. But this is not what I'm talking about. Neither am I talking about the sort of thing that might show up in a spreadsheet. What I'm actually talking about is this, an object from computer science or discrete mathematics, where you have some collection of points referred to as vertices, connected by lines, which are referred to as edges. And I think the place where the idea of a graph comes up most naturally in everyday life is in navigation. So you can imagine that if each intersection in a city street map is represented by a vertex and each street segment is represented by an edge, you can use an algorithm for finding the shortest route through a graph to find the shortest route through your city. This image in particular is from a problem that I worked on back in 2021. This is my old neighborhood back in San Francisco, and I was trying to find the shortest loop that would visit every block of every street at least once in the shortest possible distance. So a little bit more complicated than basic navigation, but still definitely a problem of graph theory. Now, what does this have to do with our problem? Well, anytime you have a set of objects and you're interested in some kind of pairwise relationship between those objects, you can represent your problem as a graph. In our case, we have the prime numbers, and we are interested in the pairs of prime numbers that have this concatenation property. That is, if you concatenate them in either order, you get another prime either way around. And so we can consider this like a graph. The primes will be our vertices, and the edges will represent pairs that have this property. Looking at the primes less than 40, we get this graph here. Now, just to make sure we understand what this is representing exactly, let's consider a particular edge. So 7 and 19 are connected in this graph. And so that means they have our concatenation property. Either way around that you concatenate them, the result should be prime. That is, both 719 and 197 are both prime. I'll just note real quick that the primes 5 and 29 don't appear in this graph. That's just because they're not connected to any of these other primes, and so I just left those out. Now, at this point, you might think that this is kind of an interesting way of visualizing our problem, but it's unclear how this actually gets us to a solution. And in order to understand that, we have to also rephrase our solution in terms of graph theory. We've already rephrased our problem in terms of graph theory. Now we have to do the same with the solution. And in order to do that, we'll take a look at the solution for the 4-vertex case, which is given in the problem statement right here. 3, 7, 109, and 673, any pair of those two has the concatenation property. And if we represent those as a graph, it looks something like this. Now, for anyone who has familiarity with graph theory, this graph in particular is going to start to set off some alarm bells. For those of you who are not familiar with graph theory, we'll need to learn a little bit of terminology first. So the first term we need to learn is the idea of a subgraph. So that's just a graph whose vertices and edges are subsets of the vertices and edges of some larger graph. And in our case, the graph we're concerned with, which is the primes, is infinite. There are infinitely many primes. And so we're almost always going to be looking at a subgraph because we humans are not very good at looking at infinity. The other term that we might use for this graph here is that it is a complete graph. That is, every possible edge in the graph is present. Or said another way, every pair of vertices is connected by an edge. And if we put those two ideas together, we get the idea of a clique, which is a complete subgraph. And in particular, if a clique has k vertices, we say that it is a k-clique. So we would say that this is a 4-clique because it is a clique of 4 vertices. So now we can restate our the solution that we're looking for in terms of graph theory. We are looking for a 5-clique whose vertices have the smallest sum. Now, fortunately, this is a famous problem in computer science. It's well known and well studied. It even has its own Wikipedia article. The problem is why this problem is famous. You see, back in 1972, Richard Karp wrote down a list of 21 particularly insidious problems in computer science and proved that they were all part of the class NP-complete. Now, that has a technical definition, but for our purposes, you just need to know that that means that the problems are very, very difficult, even for computers. And of course, if we take a look at the full list of problems, we see our problem is right there near the top of the list. Now, the one thing that is going to save us is that the problem that Karp was talking about is actually a little bit different than the problem that we're considering, in that he was looking at cliques of arbitrary size. while we're looking at clicks only up to 5 vertices. Now, when I was looking at that Wikipedia article a moment ago, you may have noticed this graphic here, which I think is an excellent representation of an exhaustive search for 4-click in a graph of 7 vertices. You can see it's basically just trying every possible subgraph of size 4 and checking each one to see if it is a click, and eventually it finds the solution down there at the bottom. And the code for doing a search like this is actually quite simple. For the 5 vertex case, it actually fits on a single slide. So obviously we still need to implement this isEdge and getVal, but other than that, this is a possible solution to our problem. There is one problem, however, which is that this algorithm as written is designed for a finite graph. You can see that this value up here, n, indicates the number of vertices in our graph. But our graph has an infinite number of vertices. Now, one solution is if we could somehow prove that there's an upper bound to how many vertices we'll need to search, we could use that subgraph as our search space, and then we would have a value for this n here. Unfortunately, there's no upper bound that I'm aware of that can be easily proven. Fortunately, there's a trick we can do in changing the way that we iterate over the possible subgraphs that will get around the fact that we don't know how many vertices we're going to have to search. And that is to, rather than pick the vertices in ascending order, if we pick them in descending order, then this works around the problem, just like this. Now, it might not be obvious that this is iterating over the same possible subgraphs as this is, and so it might actually be an interesting exercise to pause the video and convince yourself that that is the case. But once you have, you'll notice that now only the outermost loop is dependent on the value of n. And in fact, if we want to search infinitely, we could just remove that upper bound check entirely and continue to search until perhaps some other criteria is met for termination. Another possibility is that we could actually dynamically update this upper bound as we gain more information. Perhaps, originally set it to, say, int max, and as we run our algorithm and get more information about our possible solutions, then dynamically update this upper bound. In any case, this arrangement certainly gives us more flexibility than this arrangement did. The next thing that folks might recognize as a possible red flag is this quintuply nested for loop here, which suggests that we're dealing with an order n to the 5th algorithm. Now, for those of you who are not familiar with big O notation, that's just saying that the running time of our algorithm is going to be roughly proportional to the 5th power of the size of our search space. So if perhaps we had to search over the first 1,000 primes, an order n to the 5th algorithm would suggest that we would need to search 1,000,000 billion possible subgraphs. Good luck getting that to finish before I die. So how is it that this approach is even viable if we're having to search over these 1,000,000 billion possible subgraphs? Well, there's an optimization that we can make, and it relies on the observation that these edge checks here don't actually need to be inside the innermost loop. In fact, as soon as we determine the values for a particular pair of vertices, we can make that edge check. And if we move all of the edge checks as early as possible, it looks something like this. You can see now, as soon as we have the values for I and j up here at the top, we can make that edge check. And if that edge is missing, we completely skip everything that comes after that. And so that has the potential to save us billions of subgraphs that we otherwise would have had to consider. But is it enough? Well, to understand the extent to which this optimization may or may not help, we need to talk about the density of the graph. Going back to our original example here with the primes less than 40, we see that we have 9 vertices with 9 edges. And those 9 edges are out of a total possible of 36 edges. So we say that this graph has a density of 25%. That is, for any particular edge in the graph, there is a 25% chance that it is present. Note that the formula for the total possible edges is just given by the number of vertices times number of vertices minus 1, all divided by 2. So 9 times 8 divided by 2 gives us 36. And the lower the density is for our graph, the more that edge check optimization is going to help. We are in luck because if we look at how the density of the graph changes as we increase the number of primes that we're considering, we see that it drops off fairly dramatically, eventually settling down to 1.4% or so by the time we get to the 10,000th prime. Just a quick side note, I have no idea why there's this bump in the graph there. Normally when you have some oddity in your graph like that, it's because there was some kind of mistake with your experiment or your code or your math. As best I can tell, this is completely legit. If you are able to confirm or refute that this is a correct representation, I would love to hear from you. Or if you have some idea from number theory as to why this bump should exist, I would also love to hear from you. But for the moment, I have no idea. Okay, so now let's consider the implications of this graph on our algorithm. So just to get a ballpark idea, we're going to use the number 2% for our density. Obviously, as the number of primes increases past 2,000, it drops below 2%, and prior to 2,000 primes, it's potentially much higher than 2%, but just on average, 2% is a good estimate. And so that's what we're going to use for our initial calculations. So going back to our code, a density of 2% means that there is roughly a 2% chance for a given subgraph that we might have considered that we get to this particular line of code. Then there's a 0.0008% chance we get to this particular line of code. And there's a 0.000000064% chance we get to this particular line of code. And there's basically no chance we get to the innermost lines of code. So we're kind of left with this unstoppable force and immovable object kind of situation where we have this million billion possible subgraphs to consider, but then these tiny probabilities that we end up actually fully considering any particular subgraph. So who wins out? Well, I tried to come up with a model for how this might all play out, looking at the number of subgraphs that might cause us to execute a particular line of code, and then the probability that it actually does so, and then the cost of the work that we would do if we actually reach that line of code. And I'm not going to go through all the details of this, but basically when you pick reasonable values for the number of vertices and the density of the graph, we come up with something like 900 million edge checks, which seems maybe just on the edge of possible. That's certainly not ideal. But what's maybe even more concerning is, shouldn't this value be larger? That is, this is the number of value checks that we're going to be doing. And if we expect to find the solution, we should be doing at least 5 value checks, because we need to read the values of the vertices in our solution. And so this kind of suggests that we haven't even gone far enough to find our solution. So how many vertices do we need to examine before our model predicts success? That is, when does this expression for the expected number of 5 clicks actually exceed 1? Well, a little bit of trial and error is going to get you the answer that 11,581 vertices will put us just over 1.0 expected 5 clicks. And putting that back into our model, that comes out to 15.5 billion edge checks. That's not going to work. Unfortunately, there's only 2 conclusions we can draw from these calculations. One is that nobody has ever solved this problem ever. And the other one is that this model is complete garbage. Now, I actually don't know why the model performs so poorly compared to the actual performance of the algorithm. This is definitely a point at which the fact that I am a professional software engineer but only an amateur mathematician definitely makes an appearance. If anybody has an idea as to what mistake I might have made in my model, or if you have an idea for a better model, I would love to hear you comment below the video. But for now, we might just have to take away the lesson that sometimes, rather than doing a bunch of fancy math to try to figure out how your algorithm is going to perform, it's better just to write the damn code and find out. And so that's what we're going to do right now. Okay, so I've already done some of the preliminary work here, copied over our template directory, included our primes.h file for our primes class, and also copied over this isLargePrime function from problem 58 and problem 41, where we had used it previously. We'll also be using that to solve this problem. Then down here, I've copied over the code I was just showing you in the slides. Now it's fully indented. It looks a little bit ridiculous. If I were writing this for some kind of production quality code, I would probably consolidate these for loops down into one. There is a way of doing that. It makes the code a little bit more complicated, and so we'll just leave this as it is. Now, before we can actually get to writing our isEdge and getVal implementations, there are a couple of adjustments we need to make in main here. And the first one is this upper bound given by capital N. I commented earlier in the video that we don't have any number theory reason for picking a particular upper bound for our search, but we do have practical considerations for picking an upper bound. In particular, we want to avoid exceeding the maximum value of a 32-bit integer. And the largest values that we're going to be working with happen from concatenating our 2 primes. Even if they're both fairly small, the result can be a fairly large number. And so we want to double check that it's not going to exceed the maximum 32-bit value. To see how that works, let's open up our calculator. the 32-bit integer, as you might guess, has 32 bits. One of those is devoted to the sign bit, so we only have 2 that actually store value. And because of the way 2's complement works, the maximum value is actually 1 less than that. And so we want to work out what is the largest value that if we concatenate some smaller value on the right, it's guaranteed to be less than this. And if we split this number right in half, we can see that if we had the number 21,474, there are some 5-digit integers which we could catenate with that to produce a number that would exceed this. But if we have the number 21,473, then we're safe, as long as the other number is smaller. And so we're going to use this as our upper bound. So a static const int n is equal to that value. Now, this won't actually work as written because this n is a value and the vertices are being referred to by index in these loops. And so in order to make this work correctly, we actually need to do get val of I is less than n. Okay. The other thing we need to do is to actually bring our primes class into this. Any work that we do involving primes is probably going to require our primes class. And in particular, we're going to need to pass a reference to our primes class into every call to getVal and every call to isEdge. So let's just do a little bit of find replace in order to do that. We'll say getVal replace with that. Just adding the primes class reference as an argument at the beginning. And then the same thing for isEdge. Okay. All right, so the next thing we need to do is that instead of continuing our search once we have found one solution, we really just want to print out that one solution and then exit. So we'll delete this up here. And then down here, we're just going to say int solution is equal to the sum of these values. Then we'll want to print out our solution. It seems like I've got mismatched parentheses somewhere. Right here. Okay, and then we're going to say printf solution is equal to solution. And then return 0. And if we get all the way down to the end here, that means we got to our upper bound without finding a solution, and so we'll want to say no solution found. And just for our own curiosity, I think we'll probably want to print out the details of any solution that we find. So we say click is equal to curly brace, print out 5 integers, and we can just copy this and replace space plus space with comma space. Okay, that should be right. And now I think we're ready to implement our getVal and isEdge methods. So let's go up here and we'll say int getVal primes reference p. And we just say return p dot get prime. It's also going to have to take an index there. Okay. Pretty straightforward. And now we need our isEdge function. So we say bool isEdge. That's going to take a primes reference. And the indices of our two vertices. So int n, int m. Okay, so there's a number of ways that we could implement this function. In the past, we've often converted numbers to strings and concatenated the strings and then converted them back into integers. But I think it's going to be more efficient to just concatenate them by multiplying one of them by a power of 10. So let's get some powers of 10 going on here. We'll just abbreviate that PO10. We'll get the first 10 powers of 10, which are going to be 1, 10, 100, 1,000, 10,000, 100,000, and 1 million. Steal the little zeros. And we have 10 million, 100 million, and 1 billion. Okay. The other thing that we'll need is to be able to count the number of digits in a number so that we know the power of 10 that we need to multiply the other number by in order to concatenate them. Okay, so let's say int count digits, int n, and we'll have some index I, and we'll say for I goes from 1 to PO10 of I less than or equal to n increment I. That is, we're looking for the first power of 10 that is strictly greater than n, and that's going to tell us the number of digits. For example, if we had n equal to 37, we would continue searching until we get to 100 as our power of 10. 100 is the second power of 10, and so 37 has 2 digits, which is correct. Notice that we need to do less than or equal to here in order for this to work correctly. If we just did less than, then for n equals 10, we would get the wrong result because we would get to the power of 10, 10, which is equal to our number 10, and the power of 10, 10, is the first power of 10, and so we would conclude that 10 has 1 digit. I know that was a lot of 10s, but basically we need to continue searching until our power of 10 is strictly larger than our number in order to get the correct result. Okay, so now we should be set to write our isEdge function. As before, n and m here are indices, not values, and so we need to say like int q is equal to get val p comma n, and int p is equal to get val p comma m. Okay, now we need to concatenate them with, say, p on the left and q on the right. And so we need to, in order to put p on the left, we need to shift it by a number of places equal to the number of digits in q. And so we're going to say int cat is equal to p times power of 10 count digits in q plus q. And so then we say if not p dot is, oh no, we don't, almost made a mistake there. We don't want to use the primality testing in our primes class because it's actually not very efficient for large numbers. This is why we wrote is large prime in the first place. And so we're going to first check to see if cat is not a large prime. And if it is not, then we do not have an edge. So we say return false. Okay. And then we want to try concatenating them in the other way. So we say cat is equal to Q times PO10 count digits of P plus P. And then we just say return is large prime P cat. Okay, so now we should be ready to compile and run our program. Looks like I made some mistakes here. I did not actually give our array up here a type. And there's a problem on line 74. I need to actually end that line. And there we are. Okay, so let's time how long our solution takes. Hopefully not too long. Okay, we have a solution. The sum is 26,033, and we see the click printed out there. Took just under 6 seconds, so not too bad. Still not within our, I guess, preferred parameters. We would much rather have our solution finishing in under a second, especially since this problem is 20 years old, and if it's taking, 6 seconds on modern hardware, it's probably going to take closer to 2 hours on 20-year-old hardware. And so I think we can do better than this. And so that's going to be our next step, is to see how we can optimize this solution. And by far the most expensive part of this solution is the primality checks. Recall that for our large prime testing, all we're doing is just trial division. If you go up here to the top, we're just trying each of the primes in turn, dividing our the number that we're testing, and seeing if it divides evenly or not. And so this is a rather expensive operation. And the way that we've currently written our main, we're going to do the same test on the same edge multiple times. And so we can optimize our solution just by caching that result. So that's what we'll do. Let's rename this function to be isEdge uncached. And then down here, we will make the cached version, which will handle storing the results in some kind of data structure. And in particular, we're going to use a vector of vectors. So we'll say vector, std vector int. Not int, bool. Because we only need to cache whether a particular edge is present or not. And the nice thing about using a vector of bools, if we go back here for a moment, is that when we go to the description of vector on CPP reference, is we see this specialization here, where vector of bools is specifically called out for possible optimization. It's not actually required that a particular implementation optimize vector, but it is potentially optimized, usually for space-saving purposes. Okay, so the first thing that we're going to need to do is to make sure that our cache has enough rows for our indices. And actually, I lied. That's not the first thing that we're going to do, because we want to make sure that n and m come in a particular order. That is, if we have the indices, say, 1 and 3, that's the same edge as 3 and 1. But we don't want to have two separate entries in our cache just because there are two different ways of representing the same edge. And so we're going to guarantee that m is less than n by saying if m is greater than n, then we're going to swap the values. Okay, so now we can be guaranteed that m is less than n. And now we want to make sure that we have enough rows in our cache to accommodate the number that we are either looking up or adding. So we'll say if n is greater than or equal to cache.size, cache.resize to n plus 1. It has to be n plus 1 because we're going to use n to index directly into the cache. And if we only set it to n, we will barely not have enough rows in our cache. Okay, so now let's say std vector bool reference row is going to be equal to cache n. All right, so we've gotten the particular row of our cache, and now we need to fill it up at least to entry m. So we'll say while m is greater than or equal to row.size, we are going to add a new entry to the cache. And so we'll say row.pushback is edge p comma, and we want row.size and n. Okay. That should be correct. And then after we've updated the cache so that element m of row n is present in the cache, we can just say return row m. Now note that, actually what I was about to say is not correct. It's very important that we declare this as static so that on subsequent calls to isEdge, most of these lines here won't do anything because the entries will already be in the cache and it will basically just skip right down to this line here and return the element from the cache. Also this call to isEdge here has to be the uncached version. Otherwise, we'll just have ourselves infinite recursion. Okay, so let's see what happens now. Let's make, and we'll time our solution. And comes in at just about 1 second, which was at least my goal for this problem. Now, we still have one outstanding issue, which is that we haven't actually solved the problem. We have come up with a solution, but we don't know that it is the solution. And it might seem that it's not too difficult to go from finding this solution to proving that it is the best solution. But it's actually not as simple as you might think. And so in the next video, that's what I'll take a look at. How can we prove that this solution is in fact the correct solution? So I hope you'll join me for that video.